Thank you for giving this opportunity to talk. So I'm going to talk about some work on the Athermal creep dynamics of amorphous materials using a mesoscopic modeling approach. And so in the literature, you can see that there is an extensive study of amorphous material using the shear rate control protocol. So typically, you can draw the loading curve. You record the steady state stress as function of shear rate. You construct this flow curve. So from that, you can define the yielding transition point as this finite yield stress, global yield stress, when the shear rate goes to 0. So I will call, instead of what Susan called, I call this dynamic yield stress because this yielding point is probed in the steady flow state. Okay, but another protocol that is creep, which has been not paid a lot of attentions, that consists to apply a step stress onto the system. And if the stress that you apply is larger, for example, than the dynamic yield stress, you will normally hope the system will go at the end into the steady state flow of the corresponding shear rate in the flow curve. But it's not always the case. I will show with the framework of our approaches. So we will study the transient of the amorphous system from solid to liquid using this kind of protocol and using the mesoscopic modeling approach. So as been repeated several times, the plasticity of amorphous materials is updated by local rearrangement of particles, which redistribute stress and activate the other. So the model that we adopt is this picture. You share the system. Locally, there may happen plastic events, yields, redistributed local stress, so trigger another one, and so on and so on. And the stress redistribution around one plastic event is according to the Asia-based propagator. And then we adopted two kinds of elastoplastic model. The first one is a spatial one. So for each subvolume site, we associate the stress that is composed by a macroscopic applied stress, big sigma, plus the fluctuation of stress due to the heterogeneity of strain field that is coupled through this Asia-based propagator. And then local dynamics is very simple. It's like just a viscous fluid one. But then we have a local state variable n, which mediates from in between 1 and 0 to decide if locally it's an elastic or a plastic state. So in this model, the initial condition is wholly defined in the strain field at time t equal to 0. But thanks to the propagator here, we can convert this field to a stress field. So in the mean field model, we just mainly adopted the Eberholger equations with a slight modification of the shear rate to implement a constant stress protocol. In the mean field model, the initial condition is fully determined by the probability distribution of sigma at time t equal to 0. So in both models, if you ignore the spatial correlation of the stress field in the spatial model, you can actually define the initial condition of the two models into just a probability distribution of local stress at time t equal to 0. And we will consider a Gaussian distribution with a certain spread that is which can be considered as a phenomenological description of the age of the system, which is inversely proportional to the age, because if the system is well annealed, you should expect that the system is more homogeneous, so the stress distribution has less width. So the purpose of this work is study the strain response as function of the stress that you apply, and also as a function of the initial aging or annealing. So first result we checked within these two models are the consistency of the two protocols. They are very consistent, and from this logical flow curve, we extract the dynamic yield stress within these two models. And I want to draw one attention is that the dynamic yield stress of both models is actually much smaller than the local threshold of local plastic rearrangement. So then we'll go to the creep. So here I show the results on the creep. I just fix the initial annealing, so the spread of the initial Gaussian, and then I increase the applied stress. As you can see, so this column is from spatial model, this column is from Mean-Field model. First row is for the strain, the second row is the shear rate, the strain rate. And you can see that in the shear rate, you have this typical nonlinear behavior that is observed in experiments. And to give you an idea, so here is a results from Patterning suspension. You can see the similarity between this model and the experimental results. And then, so I fix the shear, the stress, and to see what is the effect of initial aging. So you can see that as aging increases, the system takes longer to fluidize, and at the end they arrive to the same state, the same plateau. And this is also consistent with experimental results reported on colloidal glass. You can see that actually there's four curves here is qualitatively agree with this. Sorry. Which figure? Colloidal glass. Okay, so before I continue, I want to make some terminologies on these curves. So there exists a microscopic time scale, so beyond which the behavior of the system is only dependent on the details of the model, which is not interesting. And then you can see for some curves, either you decrease the stress you apply or you increase the initial aging of the system. The shear rate develop the minima in the time series. So in between the microscopic time scale and the tau minima, I call it a creep regime. But for those curves, so when you increase stress or you decrease initial aging, the minima could just disappear. So some curves there that just does not have the creep regime. And in between the tau min up to the steady state plateau, I call it the fluidization regime. And in this regime, you can always define an inflection point in this time series to define the fluidization time. So the first question I want to ask is, what is the underlying process or the mechanism during this strongly nonlinear behavior? So to do that, we look closely to the mean-field model and split the epilogue equation into two populations. So the P0 is a population corresponds to the sites that has not been activated since the onset of creep, and the PM is a population of sites that has been activated during the creep at least once. So then you can write the dynamics, coupling dynamics of these two probability distributions, which actually equivalent to the original formulation of epilogue model. And we can solve that, so we can extract the contribution to the full solution, the full shear rate, from the sites that undergoes their first plastic events, or the sites, so the influence of the initial condition. So then we compare the gamma dot 0 and the gamma together. So the blue curve is a full solution, and the gamma dot 0 is the solution. So the contribution from the initial condition. As you can see, that they agree very well from the beginning up to the mid fluidization time. And here is actually corresponds more or less to the fluidization time tau f, the inflection point. So then we can interpret the tau f from the model that it's actually a time scale that characterizes the time scale that beyond which multiple activations takes over, and the memory of the initial memory of the initial condition is lost, and beyond which the dynamics is dominated by the initial state. And to study how the initial state, the initial condition gave rise of this different kinds of behavior. So we do some kind of semi-qualitative analysis. So here is the epilogue model that we use. You can see that the whole dynamics, the evolution in time of P of sigma is driven by the part of P of sigma that is larger than sigma c. So if this probability is 0 beyond sigma c, this part, the whole part is 0. And then you can see that these two terms are very close, only with a sigma here, which close to 1. So you can make some approximation to see these two quantities are approximately equal, and make an integral on both sides of this equation, and to arrive to a effective dynamics of the shear rate of the system. And here you have two terms. So the first term here with a minus sign, which is a loss term due to the plasticity, and there is a supply term, so coming from a drift that is caused by the elastic response, and a diffusion term that caused by the plastic, so the stress perturbation around plastic events. And then, so with this, we can see that we can consider three simple cases. When the first case is when the initial distribution of stress is very narrow, you have very little population that is so beyond the threshold. In that case, the supply term is always smaller than the loss term. In this case, the shear rate would just goes down. And in the opposite case, when the spread is very large, you have a large population beyond the threshold, which gives the supply is always larger than the loss, and that gives the curves that for large applied stress or for large spread in the initial condition, the shear rate just increases without developing any minimum. And in between of them, there's a mixture of the two. So in first place, supply is smaller than loss, you have a decrease, and then supply larger than loss, you have this S shape. And so with that said, so you can conclude that the behavior of a shear rate at time t goes to infinity is not only determined by the stress that you apply onto the system, but also on the spread or the initial aging of the system. So in this extreme case, when the spread of the initial Gaussian is really small, you should apply stress that it's very close to its local yield threshold to activate the system to make the system to flow, and which the local threshold I just tell you that it's very much larger than the dynamic yield stress than this value. So this suggests that there exists maybe another critical value which is larger than the dynamic yield stress one. Only when you apply a stress that is larger than this value in creep, you can activate the system to make the system flow. Okay, and this also explains the curves here that so all these curves I show here with applied stress is larger than the dynamic yield stress, and for some of them, you see for the stress that goes down, there's some of them just vanish at the end, and also suggests that the divergence of the fluidization time scale diverges when the applied stress is getting closer to the static yield stress, which is dependent on the initial aging. And this property or this behavior also manifests in this plot. So this is fluidization time scale tau f as a function of the distance to the dynamic yield stress. You can see that as the aging increases, there's a curvature upward here suggesting a divergence before you reach the dynamic yield stress. So to estimate the static yield stress and to assess the divergence, we made a hypothesis that the fluidization time scale indeed diverges in this form with two fitting parameters, the static yield stress and the exponent. And indeed, this fitting works quite well, especially for the Mean-Field model. And from that, we extract these two quantities. And then just one more word on the static yield stress. So here this is the stress strain curve that has been showed yesterday by Ludovic. Since it's a quasi-static limit, you can expect that the steady state stress is actually the dynamic yield stress. And if you start with a system that is very well annealed, and you apply a stress larger than this dynamic yield stress, but smaller than this overshoot, you probably will get stuck on the elastic branch. And then the only way that you can fluidize the system is that you apply a stress that is larger than this overshoot. So there's a close relation between the stress overshoot in the quasi-static limit and the static yield stress that you have in the creep. And then we compare these two quantities with in our two models. You can see the cross is the static yield stress and the circle is the stress overshoot. As function of this quantity, I will explain later. So you can see that these two quantities follow the same trend and actually compare rather well for the Mean-Field model. And then we measured, so in the inset is the value of the divergent exponent that falls into a range that is consistent to the experimental reported values. So this is quantity. So in the numerator, the SD just characterize the aging of the initial state, and this quantity is actually characterize the aging of a system that flows as a zero shear rate. So if you have for example, two systems that they have more or less the same initial aging state, you should expect that they have about the same static yield stress. And indeed, as this quantity goes to 1, so this one goes to 1, this one just goes to 0.5, you have the static yield stress goes to the dynamic yield stress. And then we study with the spatial model some spatial correlation of plastic events. We define for timescale t accumulated plastic event map, integral of local plastic event within a time interval around t, and do some correlation maps, and then define a correlation intensity just as the integral of absolute value of this correlation map. And you can see the results here. So as you can see, you decrease the stress. This is the shear rate curve. And you can see that the correlation intensity develops a peak at each moment, which corresponds to more or less the fluidization time scale. So actually, so we can then associate another physical meaning of this time scale is that's when during the creep that the correlation is very strong. Second point is that the correlation intensity develops a second peak, which is inside the steady state regime of shear rate. So maybe the true steady state cannot be assessed by looking only at shear rate, but after the correlation intensity develops the second peak. And then so another thing is that if you look just before t equal to 10, you can hardly tell if this one will creep or not, will fluidize or not. But if you look at the correlation intensity, you see that this curve just decreases monotonously. It can play as some role of a precursor of the fluidization. And then I showed just two maps of the correlation map and the plasticity map for the largest press stress at the first peak, and for the smallest press stress at the first peak, and they look like that. So for the small stress, which is close to the critical point, you see that there's some shear binding forming with a very strong system spanning correlation. Well, for the large stress, which is far from the critical point, the activity map is rather homogeneous, and the correlation map is, so there's some correlation, but not very strong. So to conclude that we have a model that is phenomenological, which is simple, but it's enough to reproduce the qualitative behavior in the creep. And then we can associate the fluidization time scale that characterized by the inflection point, the shear rate, to two physical meanings. So this time scale beyond which the initial state is lost, and also where there is a strong correlation. And then we estimate the static yield stress, which is highly consistent with the shear stress overshoot in the quasi-static limit. And with that, thank you for your attention. Yes.
And it is associated with specific scaling law for gamma dot as a function of time.
Yes.
You know, the so-called Andrat creep and so on. So
yeah.
do you have something equivalent here?
No, actually, so first in experiments, you do not see universal universal values of this exponent. And in our model, it's actually very dependent on how you prepare the model. So let's see. So for here, so for example, so for some curves when the stress is very large, the creep regime is even small. You can hardly define a power law. But when you decrease the stress close to the critical point, there's some power law there. But we feed these curves with power laws, and the value just varies from 0.6 to 1.2. So it's not universal at all. Yes. Thixotropic. So.
You have a characteristic time of every
Yes. So the texturotropy refers to the loop that you have in the Fourier curve, right?
You mean like a creep jammed or creep accelerated depending on
Yes.
the
Yes.
applied shear stress.
Yes. No, I don't know how to. Don't know. Anyway, I don't have texturotropy. Yeah, I'm not sure I understand the texturotropy thing, but here I don't know.